让您开始接下来的报告。
Okay.
Okay, morning everyone. Let's start the webinar today. It's our great pleasure to invite Professor Cheng-Wei Chiang to give a lecture for us. Professor Chiang obtained his PhD degree in physics from Carnegie Mellon University in 2000. He has been studying elementary particle phenomenology with particular emphasis on heavy flavor physics and CP violation, beyond the standard model Higgs physics and electroweak phase transition, various new physics models for dark matter and experimental anomalies, and recently the deep machine learning as well. He is currently a professor in physics department of Taiwan University and a center scientist of the physics division of Center for Theoretical Science at the same time. The talk title today is Phenomenological Studies of the Georgi-Machacek model. Let's welcome our speaker.
Okay, thank you very much, Ziting, for the introduction and also for the invitation. It is my pleasure to be able to give a talk. Unfortunately, due to the COVID, I cannot visit in person. Otherwise, I would be happy to meet every one of you and talk to you. Yeah, hopefully that won't be long. And okay, so today my talk is about this Georgi-Machacek model. And I know that at least one of your faculties, Professor William Cheng, is also an expert on this model. But I suppose most other people, since this is not as popular as 2-Higgs double model, so I assume that most other people may still need some background about this model. So I will spend some time. Okay, so this work is based upon this work published last year, and it was done with my former student Chen Dingguo, another master student Huang Chenzhe, and my previous postdoc, now currently the faculty member at the Huzhou University, Lu Woqiang. Why is it not working? Oh, okay. So here's the outline of my talk. So first, I will give you some motivations about why we want to consider in general, Higgs triplet models. And in particular, I will give you a quick review about the Georgi-Machacek model. And I will show you our global fit to the theory and the experimental bounds. What is the current constraints on this GM model? Then I will show you, based upon the global fit, what is whether it's possible to get sufficiently strong electroweak phase transitions. And then I will talk about the gravitational waves coming from the phase transitions. And then finally, I will show you some predictions based upon our fits and calculations. What are the important predictions of physical observables that we can possibly detect at the current and future colliders? Then I'll summarize. Okay, so first about the extended Higgs sector. So as we know, in physics, in particle physics, we have symmetries, particularly gauge symmetries, which basically guide us how we construct our models. But for the scalar sector, it seems that there's no universal guiding principles to tell us how to construct the model. For example, what kind of representations should we choose? Of course, the doublet has some advantage, or in some sense, you can say that it is necessary. But what about the other representations, singlet, triplet, and so on and so forth? And also, number of copies. How many doublets do we need? Also, how many, if there's a singlet or triplets, how many of them do we need? Right? And whether we should impose additional symmetries. It could be some discrete symmetry, so that maybe we can, from this kind of models, we can get the dark matter candidate, or there may be even continuous or even gauged symmetries, additional symmetries. But I think even though I said there's no real guiding principles, but maybe there's some at least motivations, namely the new physics motivations. For example, for the SUSY models, you know, for consistency, we need to have 2 Higgs doublets. Or as I just mentioned, if you want to have a dark matter candidate, then you may want to introduce new scalar fields. And also other motivations like to explain the neutrino mass or electroweak barogenesis and so on and so forth. In the past, a lot of people have already considered like singlet or doublet extensions of the scalar sectors. So maybe we can consider something else. Well, the next simplest one is, what about the triplet? If we want to introduce triplet Higgs fields, what are their functions and what novel features do they lead to? Okay, so if we introduce, in addition to the standard model doublet, if we further introduce a complex Higgs triplet that's denoted by delta, then it is possible to give the Majorana mass through this kind of Yukawa interaction. We can give Majorana mass to the neutrinos. Diagrammatically, it's something like this. So imagine you have a left-handed neutrino line here, and it is coupled through this Yukawa coupling with the triplet field. And then the triplet field will couple with the standard model Higgs doublet through some mu term, okay? Then once the doublet gets a VEV, then effectively you can view this as the VEV of the triplet. Then through this Yukawa coupling, this triplet VEV gives mass to the left-handed neutrinos. Therefore, it's a Majorana mass term. So this is the so-called type 2 seesaw mechanism, and the neutrino mass is roughly, well, in the simplest Higgs triplet model, it's like this. Okay, but you know there are other constraints in model building. For example, the most direct constraint is this one, the electroweak rho parameter. And there's this famous formula for the rho parameter at the tree level. So given a particular representation of the scalar field and its VEV, then you can calculate what is the contribution to the rho parameter at the tree level. Okay, and from this formula, it is easy to prove that you can add an arbitrary number of singlet or doublets without, and always get a rho at tree level equal to 1. And you know, the current data, the rho is measured very close to 1. So we don't want to violate this property. So adding singlets or doublets is fine. But what about other representations? Okay, so we are talking about the triplet representation. So let's see, suppose we add this kind of triplet with the hypercharge equal to 0. A little calculation, you will find that the rho parameter is greater than 1. So this VC means the VEV of this C field. So you will get a positive contribution to the rho parameter. And if you use this representation with hypercharge equal to 1, so this one is a real triplet, and this one is a complex triplet. In this case, turns out that the rho parameter is reduced by this factor. Okay, and if we take the current experimental bound, experimental value of the rho parameter, then we can bound these two VEVs to be something like this, just a few GeV. Okay, so this motivates the Howard, Georgi, and Machacek to consider their model in the mid-80s. So they say, oh, why don't we consider a model with both real and complex triplets, so that, and also their VEVs are aligned so that there is a cancellation between these two, so that we can keep rho parameter equal to 1 at the tree level. That's the custodial symmetry in this model. Okay, if you have any question, please interrupt me and we can discuss, right? Okay, so let me now give you some brief introduction about the model. So again, this model is the smallest, the minimal Higgs extended Higgs model that contains triplet fields and also maintaining this custodial symmetry. So here is the Higgs potential. Okay, there are many terms. I want to mention that this M1 square, the mass term for the doublet, is just like in the standard model, we assume it's negative so that it will induce spontaneous symmetry breaking. On the other hand, the mass term for the triplet is assumed to be positive. Okay, then how does the triplet get above? Well, we have this mu term that couples two doublets with the triplet. And this, we already saw the diagram for this kind of coupling before when we talk about a few slides before when we talk about the type 2 seesaw, right? So once the doublet gets above, you can change this to the doublet valve. Then you get a term linear in delta, so that you can imagine that the originally symmetric potential shape of the triplet now is tilted. Therefore, the triplet is induced a valve by this mu1 term and also the doublet valves. Okay, in this model, there is a decouple limit, namely you just take M2 to infinity. Once you take the M2 to infinity limit, then all the triplet fields will decouple from the doublet and the model will be essentially just the standard model. Okay, now again, we can write our doublet field and the triplet field in the SU2 left cross SU2 right representation like this. So the doublet is a bidoublet under SU2 left cross SU2 right, and the triplet is a bitriplet like this. Again, these three Cassie fields are the real triplets, and these chi fields are the complex triplet fields. Okay, so that we start from this, and once the doublet gets a valve, these neutral triplet fields will be induced with the corresponding valve like this. Okay, and here we have to take V chi equals V C equals, let's denote it by V delta. It's just, they should all be the same. This is required by the custodial symmetry. Okay, so the original SU2 left cross SU2 right global symmetry now is broken down to the diagonal or custodial SU2V. And this guarantees that rho equal to 1 at the tree level. Okay, now let me talk about several features of this model. One feature is that in this model, you can consider large triplet valve cases. So remember earlier when I said that if you just add a real triplet or you only add a complex triplet, the valve of that triplet is constrained by rho parameter to be less than a few GeV. But now we don't have this constraint because rho equal to 1 at the tree level. So V delta can be any value in principle. And of course, that's in principle. Of course, we have other constraints. But basically, you are allowed to consider the scenario where the triplet valve is of order 10 or a few tens of GeV, this kind of a regime. So in this case, the one consequence is that these triplets have can have larger couplings with the W boson. It should have larger couplings with the W boson and the Z bosons than to the leptons. So the other scenario is when V delta is very small, smaller than maybe a few MeV, then in that case, the triplet mostly couple to the leptons. So there are two extremes. I will show you a plot in a few slides. So this is the first feature that V delta can be large. So you may wonder how large can it be? Okay, so now let's look. This total VEV, now it's the sum of the double VEV and the triple VEV, and this is constrained to be equal to 246 squared. And well, in the literature, there are two parameterizations. In this talk, I will use 10 beta defined to be the double VEV divided by the triple VEV and some numerical factor. There's also the other notation, 10 theta h is defined as the other way around, the ratio of triplet to the doublet. So if you consider this this relation, and if you turn off the doublet VEV, namely let's assume that the electrosymmetry breaking is totally due to the triplet VEV, then in this case you will get a value of about 87 GeV. Okay, in fact, that's what they talk. These two papers talk about at that time, but just a possibility to break the electroweak symmetry. But of course, we know that we need, for simplicity, we probably still need the doublet field. The reason is very simple, just to give the usual Dirac mass to the quarks and the charged leptons. Okay, so we need this doublet VEV. And in particular, if we assume this doublet coupling with the top quark is perturbative, it cannot be too large, then that means the doublet VEV has to have a minimum, right? And in that case, the minimal possible value for phi will give us a largest possible value of V delta. So it turns out that's about 80 GeV. So that's why I said earlier that we can consider the triple VEV in the regime of a few tens of GeV. But of course, this upper bound is too loose. There are other constraints I will show you later. The second feature of the model is that there is a doubly charged Higgs boson. And moreover, this doubly charged Higgs boson can decay or anyway couple to lepton number violating processes or even lepton flavor violating processes at the tree level. Okay, so this is I think phenomenologically this is quite quite striking feature. Moreover, this provides a link between neutrino physics and the collider physics. In other words, so this model can, as I mentioned earlier, this model can explain the neutrino mass through the Yukawa coupling. The same Yukawa coupling will lead to this lepton number violating or lepton flavor violating processes. Therefore, if we observe such a particle and we observe this kind of decays at HC, that will give us information about the neutrino physics or neutrino mass. So what is the full picture or full spectrum of this model of the scalar sector? Well, here it is. So as I said, there's a triplet denoted by delta, and there's a doublet denoted by phi. And this is a bi-triplet, bi-doublet under the symmetry. And now, after the electroweak symmetry breaking, it breaks down to this custodial SU2. Then under this symmetry, these 9 degrees of freedom can be classified into a quintet, a triplet, and a singlet. Likewise, this 4 degrees of freedom can be decomposed into a triplet and singlet. Now this quintet, of course, it doesn't mix. There's no partner to mix, so it is by itself forms a physical quintet state. These two triplets will mix through the angle beta that I mentioned earlier, basically the ratio of doublet to triplet. So this mixing angle will give us a physical triplet state and the goldstone state. and the two singlets will mix through another mixing angle denoted by alpha into presumably the 125 GeV Higgs that we have observed and another singlet state. So here in our later analysis, we will assume that this guy is the lightest one. All the others are heavier. Okay, that's just an assumption. There's no particular reason, right? Okay, because of the custodial symmetry, the states in one representation share the same mass. So all of them have this mass, and all of these quintet states have this mass. Of course, this is the tree-level relation. You can consider radiative corrections, electromagnetic radiative corrections, then there's mass splitting among the states, of course. But since we are talking about the masses in the region of a few hundred GeV, so the mass splitting due to the radiative corrections is much smaller than that, typically maybe a few hundred MeV, like 3 orders of magnitude smaller. So to a good approximation, we can consider all of them to have the same common mass like this. Another thing is that this quintet do not couple with quarks. So they are quark phobic. And this triplet do not couple with the gauge bosons, the weak gauge bosons. So they are gauge phobic. So there's this feature, okay? And the neutral state here is CP even, this guy is CP odd, and this guy is CP even. So this, to some extent, it's a bit analogous to the A field in 2x double model, right? So, okay, the third feature of this model is that this 125 GeV Higgs boson can have either stronger or the same or even weaker couplings with the W and Z bosons. And I think that's the simplest model that have this kind of feature. For example, if you consider the singlet extended or the doublet extended models, the Higgs coupling to the W boson, Z boson can at most the same or weaker than the coupling in the standard model. Okay, let me show you. Here is the list of different neutral Higgs bosons couplings with the fermions or the weak gauge bosons. So you see, this is the 125 GeV Higgs. It couples with the fermion with this scaling from the standard model value. So this is similar to 2x double model. But the coupling with the weak gauge boson is given by this expression with this peculiar factor, square root of 8/3 here. Imagine you change this to 1. Then you see that this whole expression is just the sign of beta minus alpha. Then it's the same as the 2x double model. But because of this additional factor, now the whole combination can be, as I said, can be either greater than 1, equal to 1, or smaller than 1. Okay, so that's the simplest model that has this kind of feature. And this is the other singlet. So you see it's complementary to the standard model's Higgs boson like that. And another thing that I want to mention is that for these two neutral states, you can see the expression for kappa V is, by V, it refers to either W or Z. So for W and Z, they have the same scale factor. So here I define something called lambda. And so lambda WZ is the kappa W over kappa Z. Well, in general, suppose they're different. So that's why I define this lambda. But in these two cases, the lambda kappa Z, lambda WZ is just 1. So they have the same scale factor for the W boson and the Z boson. Okay. For H3, as I said, it's gauge phobic, so it doesn't couple with the W and Z, but it couples with the fermion. And H5 is quark phobic, so it doesn't couple with the fermion, but it couples with the W and Z. But now you see they have different couplings. Therefore, this lambda factor is no longer 1. Actually, it's -1/2. Okay, so that's another peculiar feature of this model, that there is such a neutral state that couples differently, even in sign, to the W and Z bosons. All right. Now, the fourth feature is that in this model, there's a tree-level coupling between the singly charged state and the W and Z bosons. So, well, H3 is impossible. Again, H3 is gauge phobic. So this is H5, the singly charged state in H5. And this coupling, again, it's, as I said, it appears already at the tree level, and it is proportional to the triplet valve. So if we consider this kind of regime, so this coupling could be interesting. In comparison, in the Twix doublet model, there is no such vertex at tree level. This kind of vertex can only be induced at the one loop level, so it's much more suppressed. Now, finally, I will show you on the next slide that the Higgs decay pattern is, well, by Higgs, I mean all the Higgs states in this model. The decay pattern is mainly controlled by the triplet valve and the mass hierarchy. Okay, let me show you. So here, this is very schematic. The horizontal axis is the triplet valve, and the vertical axis is the mass difference. Well, particularly the mass difference between the quintet state and the triplet state. Okay, so suppose we first consider region 1 and region 2, where the mass splitting is not too large. Then in region 1, the valve is smaller than like MeV. Then in this case, these states will decay dominantly to the lepton final states. Once we go beyond the MEV region to a few tens of GeV region, in this region, the most important decay modes are either for the H5, it's the gauge bosons, and for H3, it's the fermions. Okay. Now, if the mass splitting is sufficiently large, like in region 3 and the region 4, now it depends on the hierarchy. If the 3 state is bigger than the 5 state, then the 3 state will decay first into 5 state plus the weak gauge bosons, and then the 5 states will decay leptonically. Or if it's the other way around, then the 5 state will decay into 3 and the gauge bosons and so on. So that's this region 4 is similarly, it has this kind of cascade decays, right? Okay, that finishes my quick introduction to the model. Now let me just show you what is the current global fit of the model parameters. Okay. Okay, first let me tell you what constraints we impose in this for this fit. The first is the theoretical bounds, and by theoretical bounds, I'm referring to first the vacuum stability bound, meaning that we want to make sure that the potential does not have any runaway direction, so it's always bounded from below in all directions, all field configurations. Okay. The second constraint is the perturbative unitarity, and this means that we consider all the 2-to-2 scattering channels for the weak gauge bosons and the scalar bosons. Then the largest zeroth partial wave mode, the amplitude should be smaller than the real part of the amplitude should be smaller than 1/2 at high energies. So that's the unitarity constraint. And then finally, we require that the vacuum is unique. There's only namely the vacuum we found is the global minimum rather than the local minimum. So these are the theoretical bounds we impose. Then we impose experimental bounds or constraints. The first experimental constraint is from the Higgs signal strength for all the decay modes. Here in this table, we just show you for different channels, what are the inputs. So these numbers, I'm sorry, that these numbers refer to the references in our paper. Yeah, it is impossible for us to list all the values here. So we just give the references. So to show you that we take the inputs from different experiments. See, we even have the 8 TeV data or 13 TeV data. Okay, and here we just say that these data purely from 8 TeV or these data purely from 13 TeV. Okay, so anyway, so we take the measured Higgs signal strength as our inputs. We combine all these data. And then the next experimental constraint comes from direct search bounds. So you can see that there are actually many direct search channels. And again, we take them into account. And what we do is we use this package called HepFit that is available on the market. It is basically a Bayesian statistics, uses Bayesian statistics approach to analyze the data. So what it does is that first we have to assume a prior distribution for our model parameters. Okay, so that's our bias. Okay, the bias from the analyzers. But then use the Bayes rule and the input data. We perform a global fit. Then we produce a posterior. Then the package or the code will do it iteratively. So it will take the first posterior as the prior for the next run, and so after a few runs, the posterior will settle down. Then we get the final posterior probability, and we use that probability to infer other consequences. Okay. All right. So here I show you, well, I think the two of the most important parameters in the model. The horizontal axis is the mixing angle alpha between the singlet states. The vertical axis is the triplet valve. Okay. In this panel, in this plot, what it shows is that if we just impose our prior distribution, okay, that's our biased assumption, then what is the distribution on this plane? And you can see that basically it's everywhere. Of course, it has more probability, or the distribution is denser near this point. This point is just the standard model, right? Because the mixing angle equals to 0 and the valve, the triplet valve is 0. So that's the standard model limit. All right. Now, if we just, in this plot, if we just impose the theoretical constraints, namely the unitarity, vacuum stability, and so on, then the distribution is limited to this region and a little bit over here. So you see that some of the parameter space is already limited by the theoretical bounds. Now, if we further add the Higgs signal strength, then look at this plot. We are now left with only this funny shape, this banana-shaped region. And by the way, you notice the change in the vertical scale. In these two plots, it's from 0 to about 80 GeV, but in this plot, it's only from 0 to 38. So that's what I said earlier. By imposing more constraints, actually V delta cannot be too large. Now it's restricted to at most around 35 GeV. And also the range of alpha is from 0 degree to something like a minus 26, 27 degrees. Now, if we further impose the direct search bound, then the region, the parameter space is now restricted to this region. I should also explain there are some contours. The solid contour is for kappa V, and the dashed contour is for kappa F. So kappa V, for example, kappa V equal to 1 curve is this one. Okay, it's this shape, and this is 1.05, this is 1.1. And then this is 0.95 here, and also there's another 0.95 here. So you see it's symmetric with sort of with respect to this axis. This has this kind of, this is V and the U and like that. And this 0.95, 0.9 are going out like that. That's for kappa V. And for kappa F is the dashed curve. This is kappa F equal to 1 here. And then this is 1.05 and 1.1. And this is 0.95 and 0.9. So you can see that after we impose all the constraints, then we still have this kind of parameter space left allowed by data and theory. So for example, kappa V can be as large as almost deviate from the standard model almost by like 10%. Okay. On the other hand, for kappa F, well, it's mostly around 1. So I don't know what's the value here, maybe 0.96 or 7. Okay. And up here, it's maybe 1.0203. Okay. So it, as far as kappa F is concerned, it's quite close to 1. Quite close to the standard model value. But for kappa V, there's a roughly 10% of room that you can vary. All right. Okay, now let me move on to the discussion of electroweak phase transition. Okay, so we assume that the phase transition takes place at a sufficiently high temperature so that we can the one loop thermal corrections is more important than the Coleman-Weinberg potential, and also we can do the high temperature expansion. So here is the potential. This means the potential without the temperature dependence, and here is the from the high temperature expansion to order T square. Okay, and here inside here, the coefficient in front of T square contains the thermal mass contributions from different type of fields, the doublet, the complex triplet, and the real triplet, and these sigmas are given explicitly given down here. And the notation of H vector here means the phi field, C field, and the chi field, right? So numerically, we find that this H phi squared term, that's this term turns out to be the most important factor here in the thermal potential. But anyway, so let me show you this plot. Okay, this plot shows you horizontal axis is the doublet field, H phi, and the vertical axis is the triplet field, H delta. So there are two possibilities about the phase transition. So here, these contours shows that at the critical temperature, how the potential looks like, okay? So going from high temperature to low temperature, the phase transition can happen in principle, can happen in two ways. One way is this one, through this kind of through this path. Well, it doesn't really go like that, because here in the middle is the potential barrier. But just schematically, we're saying that, okay, we start with the symmetric phase, and then at around the critical temperature, it will make through this path, make a transition to the other valve here. Okay, so this kind of transition, we call it a one-step phase transition. And there's another possibility, namely, well, maybe the triplet will first develop a valve at some higher temperature, and then at a lower temperature, there's another phase transition going from this point to this point. Okay, so that's the example of a two-step phase transition, right? And finally, this dashed line to this green spot means that, okay, if we keep dropping the universe keeps dropping the temperature, the valve will further evolve from this point to the final point. As you can see, presumably this is about almost 246, and this is assumed, V delta assumed to be like around 15 GeV, just one example. Okay, so there are these two kinds of possible phase transitions that can happen.
Hi, Professor.
Okay. Yes.
Yeah. So in this part, so I think you still assume that the two triplets develop the same valve. Is that possible for these two triplets develop a different valve in this case?
That's a good question. So in principle, if we remember, we assume the custodial symmetry. So to be consistent with the custodial symmetry, the two triplets cannot have different valves. That will lead to custodial symmetry breakdown. And
yeah, but that constraint only apply at T equal to 0. If at finite temperature, we don't need to really impose this, right?
You mean at the finite temperature, we can break the custodial symmetry? Is that the point?
Yeah.
Okay, we didn't consider this possibility. Let me think. Can we do that? Yeah, I guess in principle we can, because that's before the symmetry breaking. But okay, I cannot answer. Probably cannot answer you right away. I need to think about the possibility more. But
okay.
Yeah, yeah. To answer you shortly, that yes, we assume that they have the same valve for the real and the complex triplets. Yes.
Oh, okay. And another for this complex triplet, is that possible to develop the complex phase for the valve, so we can have a spontaneous evaluation there?
Well, again, I assume custodial symmetry. So if I assume that, I think it cannot get a complex valve. But I don't know about if we relax the custodial symmetry. Yes, I think in general you can have complex valves. Yeah.
Okay. Thank you.
Yeah. Thanks. Okay. Any other questions? All right. Let me move on. So. What we do is, first we take the data. Remember, we scan using this HAPFIT. We scan our parameter space under the constraints of theoretical bounds and experimental inputs, right? And we take those parameter points, and then we try to, and then we feed into this finite temperature potential, and we try to solve for this kind of situation, namely, at some critical temperature, we can have a non-trivial valve so that the potential is the same as the potential at the origin. And also the first derivative should be 0, at the condition for the local minimum. And again, the way we solve it, we use another package called Cosmo transition. And this package tells us what is the order of the phase transition, and also it will give us the parameters about the bubble dynamics, how the so when the phase transition happens, how the vacuum bubble evolve. This is useful for our later calculation of the gravitational waves. Okay, it turns out that among all the samples that pass our HEP fit, we found there's no two-step electroweak phase transitions. This is different from Yongchen's paper with other people. We think the reason is that in our scan, the parameter scan, well, first we have included the direct search bounds. And I think in their, well, Yongchen, maybe you can correct me, but in their analysis, they didn't include this. That's one difference. Another difference is that we focus more on the large V delta space. Remember that my interest is mainly in the a few GeV to tens of GeV space, but not the small V delta space. Okay, so I don't know whether Yongchen has any comments on this or not.
Yeah, we noticed your paper claim there's no two-step phase transition in this model. So we are a little bit surprised about this conclusion. Yeah, and also you mentioned this, you focus on more on this large V delta space. And the two-step phase transition, we found mostly constraint on the smaller V delta that can pass the constraint from the current LTC.
Okay.
Yeah.
Okay, thanks. All right. Okay. So now let me show you, again, this is the doublet direction. This is the triplet direction. And so we're talking in this plot, I'm just focusing on the VEVs at the critical temperature, VC. Okay, and just show you where these doublet and the triplet VEV minimum are located in this space using the parameters that we have scanned. So first, again, just the priors is denoted by the light gray dots. Okay, so we overlay the colors on top of each other. So the first color we plot is this gray. So the gray area is down here, the whole area like that. And then we impose the theory bounds like a perturbative unitarity and the unique vacuum. Then that's this green color. So that's outside, a little bit outside here. And then we further, we add another theory bound so that all the theory bounds give us just the dark gray area here. Okay, so you see that it gets smaller and smaller. And then we add direct search, that's the red area. And we added the Higgs signal strength, now that's the orange area. And then all the constraints that we imposed in the HEP fit, now the area, the region is restricted to this light blue, okay? And then finally, we found that within this light blue, we have this area that is characterized by first order phase transition, and this bright blue area is characterized by second order phase transitions. So of course, what we are interested in is in this dark blue region. Okay, so you can see that actually the collider measurements or collider experiments can be good probes of the electroweak phase transitions in this model, because as I just argued or showed you that with these different experimental bounds, we can limit our parameter space like this light blue region, okay? In this plot, we show that because we found that somehow the M1 squared, again, this M1 squared is the mass term of the doublet, seems to play an important role in the determination of the strength of the electroweak phase transition. We first mark out this region with temperature less than 60 GeV. Because we think that we cannot trust the high temperature expansion below this region, okay? And then again, these colored points are from our parameter scan. And only within these red region can we find, not all the points, but just some of them satisfy the requirement of first order phase transition. Okay, so typically we find that this ratio can reach between 2.5 to 4 if this mass of m1 square is around here I said around the minus 2,500. Remember, m1 square we assume to be negative, so somewhere down here we can find this kind of a strong, sufficiently strong first order phase transition. Okay, so that's that. Now, finally, let me talk about, well, not finally, the next thing, let me talk about the gravitational waves from the first order phase transition. Okay, so first, what we need to do is, remember I said this Cosmos transition tells us the information of bubble dynamics, which can let us calculate this alpha and the so-called alpha and the beta parameters. And this alpha parameter basically tells us the how much energy we have to produce the gravitational waves. Okay, so that tells us the strength. And on the other hand, beta tells us the typical frequency in the spectrum. Okay. Okay, but anyway, so let me directly show you the result. The horizontal axis is the frequency, and the vertical axis is basically the strength of the gravitational waves. And here, this kind of orange or yellowish band is basically the result of a lot of curves. So for each of the point you saw earlier from the electroweak phase transition, for each point there is a corresponding alpha and beta. Then we can use those values to plot a spectrum curve. And then there are so many points that, well, we just simply draw a band rather than a lot of curves, because that will make the plot ugly and complicated, right? So that's what we get. So we have this kind of band through our scan. Oh, here I tell you that there are 2,000 data points. And up here shows the sensitivity of different experiments that they can probe. So for example, the blue one's BBO here, and the LISA is up here, and Taiji is here, this green one here. So you can see the band of our scan can touch almost all of them except for the LISA up here. So barely, well, almost reaching LISA, but not quite. So we think that there is a chance for the other experiments. Again, for some parameters, they can reach up here. The spectrum can reach up here. Yeah, then there's a chance that it will be detected by other experiments except for the LISA. Okay. Okay, so now finally, let me talk about other predictions, particularly collider predictions. Now, let me come back to this plot, the alpha and B delta plot. Remember earlier after we impose the theory and experimental bounds, we get the regions something like this. Now that we have considered the possibility of getting strong first order phase transition, then turns out that we are left with this region. Okay, so first you see that these V delta, there's a minimum of 15 to about 20 something, and alpha is sorry, yeah. Here I just refer to the red region, but totally it's from alpha is from 0 to about -20, and the V delta is from a few to about 25. But if you just concentrate on the red region, then it's roughly in this region. Okay, and again, in this region, you see that for the kappa f, it is very close to kappa f equal to 1. So it's very standard model-like for the coupling with the fermions. But the coupling with the vector bosons, there's a deviation from 1. 1 is here, and so here maybe it's about just 3 to 4% kind of deviation. Okay. So here I also make a remark. The reason that we in our scan we don't have any data showing up. This echoes what I said earlier, and also what Yongchen made a comment. We didn't get a small v delta. Okay. Okay. Another prediction is the kappa gamma gamma and kappa z gamma. Okay, so there are two different modes for the Higgs decay. So again, this gray region is our original scan that only include the theoretical bounds and the experimental constraints. And this is after the colored region is after we further impose the electroweak phase transition. So the conclusion is that there is a positive correlation between these two observables. Okay, maybe we should draw a dashed line. So here is 1, and here is 1. So standard model point is here. So most of our predictions are larger than the standard model prediction. And also there's as I said, there's a positive correlation. If we get a larger gamma gamma rate, we will also get a larger Z gamma, sorry, not rate, the coupling, okay? So that's our prediction. So it's up to the experiment to see whether that's the case or not. Okay. So here I also say, if suppose we can have a more precise measurement of these two couplings. Right now, we have some information about this one. And for Z gamma, I think, as far as I know, only Atlas gave some number recently, but CMS has not. Maybe I'm wrong. Maybe I'm not too updated. But anyway, the information about Z gamma is much weaker than the information about gamma gamma. So suppose we can make a more precise measurement, then we can, at least for this model, we can probe this kind of a parameter space. Okay. Another prediction is about the mass spectrum. Okay, so after, before we impose the electroweak phase transition, just by scanning the parameter space with the theory bounds and the experimental constraints, then we can have both hierarchies, namely H1 heavier than H3 heavier than H5, or the other way around. But what we find is that if we require sufficient strong electroweak phase transition, then we are left only with this hierarchy. Okay, that's one thing we find if we want to incorporate the phase transition. So so in this scenario, we cannot have this kind of decay process. I mentioned this because in some of the direct search, there's this kind of channel. Okay. Anyway, so this plot shows that this kind of hierarchy. So delta M13 is the mass of H1 minus the mass of H3. So and this is H3 minus H5. So you see that it's always in the positive in the first quadrant. So that's this hierarchy. And also there is a dashed line to indicate this is a line of slope 1. That means equal spacing. But you see that this tells us that it's deviating from the equal spacing. Okay, we have larger in this case we have larger splitting between 3 and 5 than between 1 and 3. Okay. Now, another thing is that we found, well, I think that these people have found quite early that in this model, if we consider the decoupling limit, then the mass splitting squared should have this kind of, approximately should have this kind of relation. The mass splitting between 1 and 3 is 1/3 of between 1 and 5. Okay. So here I use this dashed dotted line to denote this 1/3 slope here. And turns out that whether we just impose the, again, this gray area, or we also impose the electroweak phase transition, they always more or less follow this curve, even though we are not restricting ourselves to the decoupling limit. Turns out that the result satisfies this mass relation. And finally, in this plot, so let me, how should I move this away? Okay, I don't know whether you see this Zoom thing on the screen or not. So in this plot, we show that the horizontal axis is the quintet mass, okay, and the vertical axis is again the mass difference between H1 and H5. So that's the original scan, and after imposing the electroweak phase transition, you see that the H5 mass is restricted to between 150 GeV and about or up to here is 1,500 GeV. Okay. So and also there's tend to be a larger gap for the smaller mass between the singlet state and the quintet state if you go to lower and lower mass. Okay, so these are what we found about the mass spectrum of the model after the scan. Okay, and I think that's our last prediction. It's about the di-Higgs production. So the horizontal axis is the ratio of the triple Higgs coupling in our model to the standard model, right? And the vertical axis is the production rate, the di-Higgs production rate between GM model and the standard model. So you see that, again, our scan tells us that this ratio can range from like 0.3, 0.4 to almost 3. So there's a wide range in this ratio, and the corresponding prediction, it could go up to this region like that, right? But part of the region is already ruled out by the Atlas search. So that's the Atlas bound, okay? Now, if we consider the electroweak phase transition, then we are left with only this colored region, right? So that limits the range of the coupling ratio. Now it's between 1 and 2.0. So this tells us that somehow by requiring a sufficiently strong phase transition, this ratio cannot be smaller than 1. Namely, the triple Higgs coupling in the GM model must be greater than or at least equal to the standard model triple Higgs coupling. Okay, and it can go as far go up to 2. Then the corresponding production rate is given by here. You have one could have enhancement. If you go up here, mostly it's a reduction, even though you see most of the distribution is here, and it's actually smaller than the standard model production. But there's some slight chance that it's in this region, then it could be 1 order of magnitude bigger than the standard model prediction. Okay, and the reason that here in this region is smaller is, again, it's because of the destructive interference between the diagrams. Okay. Oh, one more prediction. Sorry. These plots shows the production rate in our for different channels in our model. So vertical axis show you which particular channel we are considering, okay? And horizontal axis is the mass of the H1 or H3, H5, depending on which decay mode, which intermediate state we're considering. And the gray region is after our scan, and the colored region is after we impose the requirement of phase transition. And these curves are the current upper bound from the HC experiment. So you can see that, interestingly, the parameter space or the phase space points that can give us strong phase transitions are located or distributed almost at the upper edge of the gray area. So that tells us that by trying to measure these decay modes, you can also probe whether we can have sufficiently strong first order phase transition or not. That's something we didn't expect, because the colored region could extend down here, right? But no, it's mostly in the upper left region. Okay, so I think I'm a bit over time now. Let me summarize my talk. So we have performed a comprehensive global fit for the GM model, and we imposed the theory and the experimental constraints. Then we obtain what I show you what are the viable parameter spaces. And so most of the samples are distributed around kappa F and the kappa V around these values, okay? And we have calculated under the high temperature assumption, the finite temperature potential, and we found that indeed in the parameter space allowed by the data and the theory, there could be sufficiently strong first order phase transitions, and we only find in our scan we only find one-step transitions. And then we move on to the calculation of gravitational wave spectrum, and we found we can have the peak frequency around 10⁻² to 1 Hertz, and some of the parameter space can be probed by Taiji, DeCygo, BBO, but not LISA experiment. And then we also make predictions about several collider observables. First, we find that there's only this mass hierarchy is possible because after imposing the electroweak phase transition, and we find that these two couplings have a positive correlation, and they prefer to be slightly greater than 1, greater than the standard model value. And then the di-Higgs production can be enhanced in some of the parameter space that I just showed you a couple of slides earlier. And finally, I also show you that some of the direct search channels are already close to the upper bound of our parameter space. So they should be able, the experiments should be able to probe that part of space in the near future. Okay, thank you.
Thank you very much. Very nice and complete talk. So let's see is any comment or question from our audience.
Yeah, I have some other questions. Like in the page 40, yeah, the last 40. Page.
Yes. This one, right?
So yeah, it seems the gray region start at around like a 750 GeV. What's the main constraint to have these lower mass limits here?
What's the main constraint? I probably cannot answer you that question easily because it's a comprehensive scan. All I can say is that I can only guess, probably from some particular direct search experiments. it gives this kind of constraint. So this is a result of by combining all sorts of constraints, right? So, and as I said, I can imagine that probably the most important inputs is from the direct search for the neutral Higgs boson, the heavier neutral Higgs boson.
Okay.
And then we found that it's around maybe 600 something, because this is 500, 750, yeah. So maybe 600 something. Yeah.
Okay. And in page 30, maybe the last one.
This one?
Yeah, 30.
Yeah, this is 30.
Yeah, this one. So this part I didn't fully understand the point. So you mean only those red hatched region can provide the first order phase transition, or
inside this red hatched region, but not every point. Not every point. So
yeah, then but
definitely outside
the color code.
Yeah. Sorry.
Yeah, but the color code you indicate is for the VC over TC.
Yes, the color code means that, okay, so if you like in this region, so it has a larger VC over TC, but I said in this region we cannot trust the high temperature expansion. That's why we mark out this region, right?
Yeah.
And then in the leftover region, probably this part has bigger, tend to have bigger VC over TC, but the lower part tend to have a smaller VC over TC. But all of them are above 1, right? You see, the minimum is 1. So even down here is 1. So if your criteria is that VC over TC greater than 1, then all these regions satisfy that. But here I particularly point out that around here, yeah, actually around here, that's why I pointed here. So around here, it can be as large as 2.5 to 4. Yeah, but again, not every point can have wait, let me see.
You mean like all these points can have like critical temperature, but they don't really nucleate after temperature?
Yes. Yeah, just some of them.
Okay.
Yeah.
Okay, thank you. Yeah.
Okay, thanks.
Okay, I have a question.
Yes.
Okay, I noticed that you have not mentioned about the mu-G-2 anomaly. I wonder if it's possible to just explain that anomaly just in GEM model.
Mu on G-2. Thanks for the question. I think it is not possible. I don't know of any, because one thing I know is that in the simple Higgs triple model, the mu on G-2 is in the wrong direction. So we want to enhance.
To give to explain it in the body type model, in the body type diagram, the two-loop contribution.
About two-loop, I think in that study they made some comments about the two-loop calculation, and their conclusion is it's not strong enough. I think. I never studied the G-2 in this model, partly because of that paper. So yeah.
Okay. And the other problem is I wonder if you have taking into account is the vacuum stability. But it's really stable. I mean that it's LG running, LG improved the potential. Just if it exists the other vacuum in the large phi region.
No, we didn't do the RG running.
Okay, yeah. It's important just to discuss that in Higgs. It's just it depends the Higgs math. So I wonder if it.
No, we didn't. Yeah.
Okay. Thank you.
By the way, I don't see who's asking this question.
Okay.
Can I know who was asking that question? Because
It's Fei Wang.
Okay.
Okay.
Okay, thanks.
Okay, thank you.
Any more questions?
Hi, Professor. I have one question.
Yeah. Yes.
How can future experimental searches at the LHC or other colliders be optimized to enhance the sensitivity to the pair of doubly charged Higgs boson predicted by the GM model? And what are the prospects for detecting these particles?
So wait. So here I show you, this is the current bound, right?
Mm-hmm.
So you can expect that in the near future, we probably can improve by a factor of 2 or something. So we can barely probe for the colored region, we can barely probe up here. So we can, I don't think we can fully explore down here into this region. But up here, I think in the near future, there's a chance that answers your di-Higgs question.
Oh.
And your other question is, what is the prospect of detecting these particles? The exotic Higgs bosons in the model, right?
Mm-hmm.
So I think these plots can answer the question. So we have looked at all the search channels and picked these 5 channels as the most promising. Most promising meaning that the current bound is already very close to the boundary of our predictions. So you see that, for example, this one almost touches the boundary here, and here it's already touching, right? So that's these are the most promising channels. And if you want to say what are the chances to detect these particles, of course I cannot predict what's the chances. But let's say, suppose this curve, this blue bound gets smaller, gets lower, then and we don't see anything, then that just constrain the model stronger and stronger. That's usually the case.
Okay, thanks, Professor. I have another question. What is the impact of the GM model on beyond the standard model physics, particularly with regards to dark matter and neutrino masses?
The impact on dark matter, well, there's no impact on the dark matter because our model does not provide such a candidate. In this model, there's no dark matter candidate. So we don't address that question. But for the neutrino, as I explained in the beginning, actually this model was motivated to explain the neutrino mass. But again, what is the impact? There's no direct impact except I mentioned a point. Let me go back quickly. Yeah, except this point.
Okay.
I mentioned that suppose we discovered such a, for example, the doubly charged Higgs boson at the collider, and we measure and we found that it can lead to some lepton number violating or even lepton flavor violating processes, like suppose the doubly charged Higgs decay into a mu plus and a tau plus, for example, let's say. Then by measuring this kind of process, we can fix the Yukawa coupling, and from the Yukawa coupling, we can infer the neutrino mass because they have the same, it's the same coupling here that is used to explain the neutrino mass, and also the same coupling to that lead to the process, the lepton number violating or lepton flavor violating process that I just mentioned. So that's the connection. It's all through the same Yukawa coupling here. Does that answer your question? Okay.
Okay, thank you very much.
Yeah, thanks for the question.
So any further question?
Hello, may I have a question?
Please.
Yes, please.
Hello, Professor. Here is
Yeah.
Xiaotangdu. Thanks for your very nice talk.
Thank
I
you.
have yeah, I have a very naive question about the GW signal.
Gravitational wave signal. Okay.
Yeah. From the picture, it seems the frequency can reach the 100. So is there a possibility to detect the signal by the LIGO or LIGO? Yeah, this picture.
You mean 100 here?
Yeah. The h square omega GW is minus 21 or 22. This should be detected by Virgo or LIGO. Is there a possibility to detect this signal by the LIGO or Virgo?
I don't know. Is that correct that the LIGO can probe this region? I don't know. Apparently, we don't show this in this plot.
The most sensitive signal region should be 100 to 300 frequency. I think.
So that's a bit outside this plot, right?
Yeah. Maybe
but
maybe I was wrong. Maybe I'm wrong.
Okay, I don't know the experimental status, whether they can probe this region or not. Are there any experts in the audience that can answer this question?
Maybe I make mistake.
I think when we made this plot, we already considered the different experiments, and we found that these are the only relevant ones for our case. But again, you may be right about LIGO. I have to look up the references to see which frequency region they can, and also what kind of sensitivity they can probe.
Okay, thanks for answer, Professor.
Okay, thanks.
Any other questions? But Jiang, I have a question. So
yes,
in the GM model, we already know there's a strong first order phase transition. Is it possible we can find out the CP violation source in this model, or any way to extend this model or modify this model to the CP violation source such that we can explain a matter-antimatter symmetry issue?
Thank you for the question. Okay, so in this original GM model, there's no CP violation. All the parameters in the Higgs potential have to be real.
Yes.
Again, that's part of the consequence of the custodial symmetry. And recently, Professor Kei Yagyu and my former student Dean Chen and myself, we wrote a paper. I think we just put out last month or something. We recently wrote a paper to extend the GM model to incorporate CP violation. Yes,
okay.
So it is possible to consider CP violation, but you have to go beyond the original GM model, because the original GM model, in other words, you have to break the custodial symmetry from the very beginning. Yes, then yes, you can consider the CP violation in the Higgs sector. Yeah, but whether we can explain the matter-antimatter symmetry, that's a separate issue, and we don't have an answer yet.
I see. Wow, that's interesting. Thank you.
Thanks.
Any other question? If no further question and comment, let's send Professor Chiang again.
Okay, thank you all. And again, I hope that there will be a chance in the near future for me to visit Nanjing, particularly Nanjing Normal University, because I've never been there. And yeah, thank you.
Yeah, great. Yeah, we hope you can visit us soon.
Okay.
Okay, see you.
Okay, bye.
Bye-bye.